Hi guys, welcome to Group 2's group presentation on resonance. During this video, Shannon and Shay will go through the history of resonance, its founding fathers, and some of the indicators that led us to believe early on a theory like this should exist. Alex will then go through the theory of resonance inside of benzene rings. It's one of the more simple ones to explain, to grasp the concept at the beginning, as well as being one of the most common in syllabi across the country for science. Thomas will then finish off by doing some calculations, giving some visual representations of resonance hybrid forms, and as well as explaining the current theory as we understand it today.
Friedrich August Kekule in 1865 put forward a benzene structure that had shown that it had single and double bonds in a 6-carbon ring. This idea came from a dream he once had about dancing atoms. The image was of a snake eating its own tail, showing a cyclic bond within the atoms. However, it was only partly correct as it didn't explain the reason for benzene having an equilibrium. Albert Laudenberg, his student at the time, said that because benzene only had one isotope.
You could have.
The discovery of resonance was a huge breakthrough in the field of chemistry, as it took a deeper look into the bonds and delocalization of compounds. This gives us a greater idea and understanding about the makeup of the world around us. It was first introduced in 1899 by German chemist Johannes Fehl. The concept of resonance was discovered as a part of Fehl's partial valence hypothesis, as he was trying to explain the strange stability of benzene due to its single and double bonds. As a result of this, resonance was very useful in determining isomers of benzene. This area was researched due to benzene not acting like most alkenes and undergoing substitution reactions instead of addition reactions. In 1926 was the year that the mechanism of resonance was introduced to quantum mechanics. The man who introduced the concept was German physicist Werner Heisenberg. This came from the discussion of quantum states of helium atoms. Heisenberg then went on to win the Nobel Prize in Physics in 1932 for his work within the field.
Werner Heisenberg in 1926 was the first to introduce the idea of quantum mechanical chemistry, which had many incorrect ideas. The quantum mechanical chemistry showed that an electron is in between two hydrogen cation nuclei, not in one nor the other. However, Heisenberg combined the ideas with Niels Bohr to apply it to the model of atoms, and thus leading to Linus Pauling developing on resonance within bonds. Linus Pauling showed the theory of resonance in the nature of chemical bonding, 1931 to 1933. Pauling published that rather than the structure of benzene being of alternating bonds, that in fact the bonds would be in all places at once, introducing resonance as we know it today.
I will be talking about the idea of resonance in benzene and other aromatic compounds. As Pauling discusses here with the structure of carbon monoxide, the principle of resonance also explains the true molecular structure of benzene. As discussed, resonant forms explain that electrons have no fixed position in atoms and illustrate areas of higher electron density. Benzene, a 6-membered hydrocarbon ring with 3 double bonds, can be represented by 2 structures that are equivalent in energy. In the resonance model, the molecular configuration of benzene is a combination of all structures at once, with each carbon-carbon bond energetically equivalent. Benzene is a planar molecule, and the idea that the electrons in benzene is that the electrons are within the pi orbitals of the bonds, which would normally contribute to the double bond, and are located in a delocalized ring above and below the plane of the molecule, as highlighted in this picture. You can see in this representation The p orbitals share decentralized electron density. These delocalized electrons in their benzene ring make the molecule very stable and give it characteristics of a nucleophile. Benzene was discovered by Michael Faraday in 1825. However, the hexagonal structural formula didn't become conventional formula until it was proposed by German chemist August Kekule in 1865. His structure showed the alternating double bonds and single bonds within benzene. In 1931, Linus Pauling suggested his resonance theory as an explanation for the stability of the molecule. This theory explains the reasons why benzene's reactions are mainly electrophilic substitution reactions. He also concluded that benzene was stabilized as a result of the resonance of multiple canonical structures, and that the final molecule was a hybrid of the contributing resonance structures, with a constant electron distribution in time, and which cannot be represented by a discrete description. He also concluded that the resonance structure was responsible for gain in stability, called the resonance stabilization energy. The value of this is positive 143 kilojoules per mole, and means that the overall hydrogenation enthalpy of benzene is more endothermic than that for a theoretical molecule of cyclohexatriene. This gain in stability occurs because of a continuous pi bond of delocalized electrons, as opposed to being localized between two carbon atoms. Spreading the charge more evenly this way causes the molecule to be more stable and at lower energy level, as more energy is required to break the C double bonds that are found in other molecules. Thank you for listening.
Resonance is a method within valence bond theory that describes the delocalization of electrons within a molecule. It is a way that valence structures can be more accurately represented. It does this by using two or more Lewis structures to give an average structure, or what is called a resonance hybrid. This is a more realistic depiction of the structure. Resonance theory can only be applied to structures with at least one double bond. An example is sulfur dioxide. It has two Lewis structures, and from the image we can see that the double bond could be between the sulfur and the oxygen on the left, or the sulfur and the oxygen on the right. The resonance hybrid is the average of these structures. As seen on the slide, there are no double bonds. Instead, they are in between double and single bonds, and have a bond order of 1.5. This can be calculated as the double bond is then split across both. Another example would be nitrate, which has three Lewis structures that make up the hybrid. As you can see, the double bond could be from the nitrogen to any one of the three oxygens. In this image, we see that there is no double bond, as the electron density is shared across the three, giving a bond order of 1 1/3. Due to the electron density being shared, the more structures that make up the hybrid, the more stable it becomes. If we went off just Lewis structures, we would be under the impression that there are different formal charges on the oxygen in nitrate, one being neutral, this being the one with the double bond, and the other two having a -1 charge. In reality, the formal charge is the same across all three oxygens, and they are identical.